Hello guys, in the last video we have seen the laws of simple pendulum, and before that we saw the time period of simple pendulum. Now here I always say that we have certain assumptions in the simple pendulum, like there is no friction at the support, or then there is no air resistance, or the string is inelastic, it is inextensible, the string is massless, and so on. So when we consider ideal conditions, the oscillations of the simple pendulum, they should go on forever, right? But then does it happen in practice? It doesn't. And the reason is there is air resistance, correct? There is friction at the support, the string is not completely inelastic, and so on. So there are these practical conditions. We need to consider those, okay? And that is the reason the oscillations of a simple pendulum, they die out, okay? Or then you can take this example of scale. You take a scale, okay, place it on your desk, okay, near the edge, press your palm on one end, and you just put the other end into vibrations, just like this. So the scale, it goes on vibrating, but then after some time the vibrations die out. And what is the reason? There must be some reason for that, right? There's something called damping, which is stopping the oscillations or vibrations, right? We need to consider that, okay? Maybe we can take this example of a spring mass system. I have this rigid support, and this spring is suspended from this support, right? Now here we are going to put one mass M. Now obviously, initially, before I suspend this mass, the length of spring might be little less than what it is now. And once I place this mass, then under equilibrium, the spring will, it will still get extended a little, length will increase, and now this is the normal position, okay, under the action of this weight of this mass, okay. Now here suppose I pull the mass down and release it. What do you expect to happen? I am pulling it down and releasing it. So the spring force, it will pull it back towards the main position, and then it will go up and down and up and down and so on. So the mass will be set into vibrations, correct? So that is what happens, and eventually this these oscillations, they are going to die out because of air resistance and all other factors, okay? Now I want to introduce something more to this, okay? I will attach this rod to this mass, okay, and on the other end I'll have a flange, okay, and then this whole thing is submerged in some liquid, maybe some oil, some engine oil, something like that, some viscous fluid here, okay, and it will be here like this. Now again, I'm going to do the same thing. I'm going to pull this mass down and release it. What happens? Because of this spring having a spring constant K, okay, the mass will tend to move up and down. It will tend to oscillate. But now let us come to this rod and this thing. I'm calling this vane. Now what is this vane? It's V-A-N-E, okay. This part, that rod and vane, is something like this. It is some disc here and this rod, correct? This is the rod, maybe at the center. Now what happens here? When the mass wants to come down, okay, this vane has to push the liquid away, right? This has to push the liquid down, okay, But now because of viscosity and because of maybe elasticity of that liquid, elasticity, okay, uh, there will be some resistance offered to the downward motion of this vane, isn't it? So that will oppose the downward motion. And when this mass is pulled up by the spring, okay, again this will experience some force or some resistance from the liquid, correct, from the fluid, because of its viscosity. Now I'm not going to call this vane V here, okay, because I want to use V for something else. Okay, I'm going to call this vane B. Okay, now what kind of forces are there? One force is the spring force, and this other force, that other force is because of the fluid or because of the liquid, correct? And that force is damping. It is damping the oscillation. It is opposing the oscillations. So the second force is Fd. I'll call it Fd, and that is the damping force. Okay. Obviously, if the spring has got constant K, then my spring force is equal to minus Kx. And what about this damping force? Now this damping force, it is found to be equal to B into V, B into small v. Again, that damping force is opposing the motion, okay? But then, what is B and what is V? Now B is called damping constant of that liquid or damping constant of that fluid, okay? Let me call it fluid because sometimes even gases will offer resistance, correct? So let us call it fluid. Fluid can be a gas or a liquid, something that can flow, okay? This B is damping constant, and V is the velocity of the mass and this vane, okay, and V is the velocity, correct? Now by Newton's second law we know that force is equal to mass into acceleration, isn't it? So I have my net force would be equal to spring force plus damping force, right? And therefore my mass into acceleration is equal to spring force is minus kx and damping force is minus b into v. So I can say that ma plus bv plus kx is equal to 0, correct? So mass into acceleration plus damping constant into velocity plus spring constant into displacement, that is equal to 0. That is what I get here. But then how do we solve this? We need to solve this for getting the expressions for displacement, okay? Now for that purpose, we need to write this in the form of a differential equation and then solve the differential equation. How do we do that? Now acceleration, it is the second derivative of displacement, velocity is the first derivative of displacement, and then displacement, right? So let us write it like this: m into d2x by dt square plus b dx by dt plus k into x is equal to 0. This is the differential equation for damped oscillation. Okay, we had differential equation for simple harmonic motion. We solved that differential equation to get the expressions for velocity and displacement. Okay, now here we have a different kind of differential equation. Over there we had only acceleration and displacement, but we have now first derivative, second derivative, correct? We have both of them. How do we solve this? Now this particular part will be actual solving of this kind of differential equation that I will be doing in calculus, okay, solving differential equation in calculus, and over there will be actually able to solve it. For now, I'm just going to write the solution to this differential equation. Okay, so now here my solution is, I'll just cut this. So my solution is x is equal to, I'm finding the displacement, okay, it is a, okay, into e raised to minus bt upon 2m, a into e raised to minus bt upon 2m into cos of omega dash t plus phi. Does it look little complicated? It does, because if I compare this with what I had earlier, my equation was x is equal to a sine omega t plus alpha. But now again, if you try to compare this, what is the difference here? Here, this is a simple harmonic motion. This also looks like simple harmonic motion, but then there is some difference here. Okay, this sine function and this cosine function wouldn't be much of a problem. The problem or the difference here is in this. Okay, in my damped oscillation here, what is my amplitude? Amplitude is equal to a into e raised to minus bt upon 2m. So now what is a? A is the amplitude, original amplitude, the distance through which I am pulling this mass down. Okay, a is the original amplitude. Okay, now if this had not been a simple, had not been a damped oscillation, it would have been something like this: x is equal to a sine omega t plus alpha. But it is a damped oscillation. Now here it is quite obvious, right? It is quite obvious that my amplitude, this amplitude is decreasing exponentially. You see this negative sign here, okay, negative sign there, and b into t. So this, this damping, this amplitude of damped oscillation, it depends on time, it depends on the damping constant, and of course the mass. Correct. Greater the mass, smaller will be the amplitude, right? Or smaller will be the decrease. Correct. Now that you can figure out, but then the difference between this amplitude and this amplitude is this amplitude decreases with time. Okay, but then there is one more thing here. There is something called omega dash here. Here I was having omega. Had it not been a damped oscillation, the amplitude or angular frequency of the oscillation would have been omega. But now here it is omega dash. And what is that? It is root over k by m minus b upon 2m square. Okay, so this is the angular frequency of damped oscillation. Now if this is omega dash, then what would be the time period? Time period is 2 pi upon omega dash, correct? So that would be 2 pi upon root over k by m minus b upon 2m square. Okay, so this is the time period of our damped oscillation. This is my angular frequency of damped oscillation. This is our amplitude of damped oscillation. So these are the three things that we would get here, and this is of course the differential equation of damped oscillatory motion. Okay, I have said that this amplitude decreases exponentially with time. Okay, and what about this regular SHM? It is a sine curve, regular sine curve, but then this is also a cosine curve. Okay, so damped oscillation will also be a harmonic function, but then there will be some difference in that. Now let us try and sketch the graph of this damped oscillation. Okay, I'll just clear this. I'll keep that part for you to see, but then I'm clearing this. I hope this is clear, and maybe you can get this in the notes. Notes on the blog, which would be mentioned in the description. So if we have the amplitude and time here, amplitude here, we say that the amplitude is decreasing exponentially. Okay, so that means initially, suppose my amplitude is like this, then it will be like this. It's like you just see this. Now you can see here, can this be ever 0? Can it be 0? It won't, because a into e raised to power minus bt upon 2m. Okay, a into e raised to power minus bt upon 2m. So that is equal to it is as good as a upon e raised to bt upon 2m, correct? So as your t increases, okay, the amplitude will still be it will be still having some value. It will never reduce to 0. It will reduce to 0 at infinity. Okay, but practically we say the oscillations, they die out. Okay, so this is going to be something like that. You see here that exponential nature of decrease of amplitude. So that was about damped oscillations. In the next video we'll be talking more about nature of oscillations. The oscillations can be free oscillations, they can be forced oscillations, they can be natural oscillations, they can be damped oscillations, right? Till then, goodbye. Thank you so much.